I'm really happy to be able to introduce to you the idea of CoVEGI, which is the idea of cooperative verification via externally generated invariants. As already introduced, CoVEGI is joint work from me and my supervisor Heike Wehrheim, and was originally published in the last year's phase. So as this is a quite broad conference, I thought it's a good idea to start with a short introduction on what is software verification in general and what is the idea of software verification in general. So in software verification, we have mostly the setting that we have on the input side. We have a program. In this setting of my work, we assume that this program is a C program, but this is not really the important fact. And we have a property, and the task of the tool, which we call verifier, is to check if the program satisfies the given property. And the property could be, there are several ways to define properties. We focus on reachability, which means that the property says that there are certain locations which the program should not reach. And the task of the verifier is then to check if the program, or if there are some inputs or some return values to random functions such that the program reaches this specified error region or not. And if the verifier finds such inputs, then the task is to say, okay, the program does not satisfy the property, and then it can output a concrete counterexample. And if the program matches the properties, then it says, okay, it's matched, and it should output a witness, which is some kind of information. Mostly these are predicates or invariants, which makes which allows others to verify that this result is really true, because only saying yes or no is not really trustful. So to increase the trust, most of the tools also output some more information to verify that. And if we would have this situation all the time, so we have a verifier that is always say either yes or no, then everybody would be happy. But that's of course not the case, because there is a third outcome, which is called unknown. So due to several reasons, either the verifier takes too long because the task is too complicated, or the theory it is using, so for instance, it does not use the right logic, something for that, it might output unknown, which says I cannot solve the task and I don't want to guess, so I don't know, which is really an unsatisfying situation, especially for those people who verify their tools. So now I want to say or explain to you what is the idea of cooperative verification. So the good thing is, if we have kind of these situations, we have a variety of tools. So on the one hand, we have a tool or a verifier which we believe is a good one, which can work quite well on loops. So for the program loop C, it is able to verify that correctly and find a witness, but it does not handle recursion correctly, or it's not really strong on that. So if we give it a program which contains some recursion, the verifier will output unknown. The good thing is we are now able to have, or there are a lot of other techniques and hence other tools which implement these techniques. And the other technique is able to not fully solve this task, but we assume it is able to generate some helpful information. These are, in this case, loop invariants, and we can then, these information are then helpful for the verifier. So what's happening? The natural thing is, what's happened in the past a lot is people or tool developers in general, they integrated these other techniques. Either they re-implemented this, which is obviously not the best way of doing this, or they built a hardwired connection and had a white box integration to just be able to work with this specific other technique. And the idea of corporate verification is not to have this white box integration, but to have a black box cooperation between two or several tools or ideas, more generally, to share information and to be able to solve this task while cooperating. And the idea of CoVEGI is one of the first ideas to show how this cooperative verification can look on a specific example. And the idea is to have the cooperation between these two tools, so the verifier and the other technique, which is able to generate information, generate invariants. So What do we need to do that, and more especially, what information do we need to exchange? So in CoVEGI, we foresee two components. The one on the left-hand side is the main verifier, where we have one component of which we assume is a good tool, which is able to solve a lot of tasks by its own, but has some drawbacks. Let's recap that. For instance, it's not able to handle recursion or floats or whatever. And then on the right-hand side, we have several helper invariant generators, which generate invariants, which are not, we don't require them to solve the task at all, or the full task, but they just need to generate some invariants. And in addition, we do not even require that these invariants are completely correct, but they just should contain helpful information. So which information are then exchanged between them two? Okay, quite simple and straightforward. The first that needs to be exchanged is the task. So the main verifier somehow needs to tell the invariant generators which is the task, which is the program, what are the properties they should generate some invariants for. And the helper invariant generator will generate, as the name suggested, invariants. And the question is, do we need anything else? Yes, we have another specific requirement. We have another capability of the main verifier, and it should be able to have something which we call witness injection, or a component or part of that should be called witness injector, which means we are able to, if we have generated invariants, these should be somehow, or the main verifier should somehow be able to take these invariants and put them into its internal analysis and internal state. So how does everything work out? What is the idea of this cooperation? So as I said before, we believe that this main verifier is a strong tool. And for now, we assume we have a pool of helpers, so we don't care how many of them there are there. We just can talk to them all at once. And initially, we start this main verifier standalone because, as I said, we believe it's a good tool and it will solve most of the tasks on its own. And let's assume that the main verifier is not able to solve the task on its own. So eventually it realizes, but is realized that the main verifier needs some support, and then it sends a so-called request for help, which is then given to the pool of helpers. And the pool of helpers and the main verifier are then run in parallel, because if we send this request for help and it was a little bit too early, then and the main verifier finds a solution 1 second after that, we want to output that solution and can then ignore the other tools. So how do we realize that? Right now, this request for help is realized by a static timer. So we give the main verifier a time budget, which it can run on its own, which is in the experimental setting, or the best one was 50 seconds. And after that 50 seconds, we say, okay, if you cannot solve the task within that time limit, then you need help. Conceptually, we can think of other ideas, so we can monitor the analysis of the main verifier's behavior and say, okay, we see something which we think, where we say the probability of solving that task is quite low, so then we send this request for help. And then we have the tools running in parallel, and the pool of helpers can compute the invariant in parallel, and eventually they will return them. And for now, we can say, okay, either we say we wait for all of them to complete the task, or we say we take the first result which we found. And in the experimental setting, it has turned out that taking the first computed result is the most beneficial idea, or yeah, at least the most beneficial. And then we have, as already teased, this witness injection step, where we either take the invariants and inject them into the running main verifier's analysis. In the implementation, we use as main verifiers the techniques k-induction and predicate abstraction. And we implemented for both witness injection, where you can put these information into the running analysis, but we also thought of restarting everything. So saying the main verifier gets as additional input these invariant witnesses, and it has turned out that this is beneficial compared to injecting it into the running analysis, because the main verifier computes a lot of information which are not really helpful, and it's all carried all around, and then starting from scratch with a fresh instance is beneficial. And then finally, the main verifier will compute a final result and return that. So that's the idea of CoVEGI. And one thing which I haven't talked about is we now have a task and we have an invariant, and we for now assumed, or I implicitly assumed, that every tool, every helper invariant generator is able to understand that task and is able to generate an invariant. We require that these invariants are in a specific format, where we use the standardized format of correctness witnesses for. And the question occurs, we ask ourselves the question, what happens if tools do not speak the same language, which is meant, like if we have a tool which is not able to work on C, for instance, because we have a task in C, and what is if we have a tool which is only able to work on LLVM? So therefore we foresee two components. With the one is called mapper, which takes this task and transpiles that into an LLVM task. It could be also some other modifications, but we implement that for an LLVM task and gives that now to the helper invariant generator, and then the helper invariant generator will compute some kind of an invariant prime. And now we need a second component, which is called adapter, which takes this invariant prime and transpiles that computes an invariant witness for that. Because the helper invariant generator number 2 only gets information in an LLVM task, so it will output an answer which contains invariants which are over the LLVM variables. So therefore we need this computation and map the information back. And then we are conceptually able to use any kind of tool which generates invariants. So let's come to the implementation and then shortly to the evaluation. We implemented everything, although we implemented the main verifier within the CPA checker. As I already said, we used k-induction and predicate abstraction for that. And we used a pool of helper, wherefore we used Wehrheim's Ultimate Automizer and Seahorn. And some of you who are familiar with these tool names might ask themselves, why do you use these tools? Because Wehrheim's Ultimate Automizer and partially Seahorn are in fact verification tools, so they can solve the task. And we realized there is no pure invariant generator available which only solves the task like this. So all of these tools are somehow verification approaches. So we used them to show that the idea of CoVEGI is feasible at all. Let's get to the evaluation. I evaluated that, or we evaluated that in the on a subset of the SVComp task, which is an annual software verification competition. And we used a subset of 342 tasks which contain loops. We used the SVComp setting, which means we have a 15-minute CPU time limit per task. And there you can see that for both tools, so for k-induction, which is standalone able to solve 144 tasks, and for predicate abstraction, which is standalone able to solve 116 tasks, we can increase increase the performance of these tools if we use a single invariant generator helper, for instance, Ultimate Automizer and Wehrheim, by around 12 to 14% with respect to the number of correctly solved tasks. And then the question occurs, what is about the runtime? So how does the runtime behave? Therefore, I brought this chart, which on the x-axis contains the runtime of k-induction running standalone for a correctly solved task, and on the y-axis contains the runtime which is taken by CoVEGI if you combine k-induction with the tool Wehrheim. And in this red dotted bar or box, this is everything which happens within 50 seconds. And for this, we can observe that both tools behave equally, which is what we expected, because within the first 50 seconds, k-induction and CoVEGI in fact behave equally, because as I said before, if the task is not solved within 50 seconds, then we start and start the invariant generation process, and beforehand it's only standalone tool. And then what we can see is, okay, we have so it takes a little bit longer for the combination, which is quite obviously because if I run two tools in parallel, then both consume a little bit more CPU time, but we are able to solve more tasks, and the effect is not really significant. And then at the third question, we ask ourselves, is it beneficial to use more than one tool in parallel? So for now, we only used one master or main verifier and one helper invariant generator. And it turns out on the data set, it is beneficial to use Ultimate Optimizer and variables in parallel, but not use more, because we have a time limit which is limiting the CPU time which is available in reviews. More than 2 tools, then each tool they steal the verification time. So to sum up, I presented you a concept for cooperative verification, which uses externally generated invariants as exchange, and it shows in the evaluation that CoVEGI can increase the effectiveness of the verification process by 12 to 17%. So thanks for your attention. I'm happy to answer your question.